Hey everyone, welcome to Ncert audiobook. Group 2 elements alkaline earth metals. The group 2 elements comprise beryllium, magnesium, calcium, strontium, barium, and radium. They follow alkali metals in the periodic table. These, except beryllium, are known as alkaline earth metals. The first element, beryllium, differs from the rest of the members and shows diagonal relationship to aluminium. The atomic and physical properties of the alkaline earth metals are shown in table 10.2. 10.6.1 Electronic configuration. These elements have 2 electrons in the s orbital of the valence shell. Their general electronic configuration may be represented as noble gas Ns2. Like alkali metals, the compounds of these elements are also predominantly ionic. Atomic and ionic radii. The atomic and ionic radii of the alkaline earth metals are smaller than those of the corresponding alkali metals in the same periods. This is due to the increased nuclear charge in these elements. Within the group, the atomic and ionic radii increase with increase in atomic number. 10.6.3 Ionization enthalpies. The alkaline earth metals have low ionization enthalpies due to fairly large size of the atoms. Since the atomic size increases down the group, their ionization enthalpy decreases. The first ionization enthalpies of the alkaline earth metals are higher than those of the corresponding group 1 metals. This is due to their small size as compared to the corresponding alkali metals. It is interesting to note that the second ionization enthalpies of the alkaline earth metals are smaller than those of the corresponding alkali metals. 10.6.4 Hydration enthalpies. Like alkali metal ions, the hydration enthalpies of alkaline earth metal ions decrease with increase in ionic size down the group. The hydration enthalpies of alkaline earth metal ions are larger than those of alkali metal ions. Thus, compounds of alkaline earth metals are more extensively hydrated than those of alkali metals. Example, MgCl2 and CaCl2 exist as MgCl2.6H2O and CaCl2.6H2O, while NaCl and KCl do not form such hydrates. 10.6.5 Physical properties. The alkaline earth metals in general are silvery white, lustrous, and relatively soft but harder than alkali metals. Beryllium and magnesium appear to be somewhat grayish. The melting and boiling points of these metals are higher than the corresponding alkali metals due to smaller sizes. The trend is, however, not systematic. Because of the low ionization enthalpies, they are strongly electropositive in nature. The electropositive character increases down the group from beryllium to barium. Calcium, strontium, and barium impart characteristic brick red, crimson, and apple green colors respectively to the flame. In flame, the electrons are excited to higher energy levels, and when they drop back to the ground state, energy is emitted in the form of visible light. The electrons in beryllium and magnesium are too strongly bound to get excited by flame. Hence, these elements do not impart any color to the flame. The flame test for calcium, strontium, and barium is helpful in their detection in qualitative analysis and estimation by flame photometry. The alkaline earth metals, like those of alkali metals, have high electrical and thermal conductivities, which are typical characteristics of metals. 10.6.6 Chemical properties. The alkaline earth metals are less reactive than the alkali metals. The reactivity of these elements increases on going down the group. 1. Reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. However, powdered beryllium burns brilliantly on ignition in air to give BeO and Be3N2. Magnesium is more electropositive and burns with dazzling brilliance in air to give MgO and Mg3N2. Calcium, strontium, and barium are readily attacked by air to form the oxide and nitride. They also react with water with increasing vigor even in coal to form hydroxides. 2. Reactivity towards the halogens. All the alkaline earth metals combine with halogen at elevated temperatures, forming their halides. Thermal decomposition of NH4 Cahol to BeF4 is the best route for the preparation of BeF2, and BeCl2 is conveniently made from the oxide. Third, reactivity towards hydrogen. All the elements except beryllium combine with hydrogen upon heating to form their hydrides MH2. BeH2, however, can be prepared by the reaction of BeCl2 with LiAlH4. 4. Reactivity towards acids. The alkaline earth metals readily react with acids, liberating dihydrogen. 5. Reducing nature. Like alkali metals, the alkaline earth metals are strong reducing agents. This is indicated by large negative values of their reduction potentials. However, their reducing power is less than those of their corresponding alkali metals. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to large hydration energy associated with the small size of Be2 plus ion and relatively large value of the atomization enthalpy of the metal. 6. Solutions in liquid ammonia. Like alkali metals, the alkaline earth metals dissolve in liquid ammonia to give deep blue-black solutions forming ammoniated ions. From these solutions, the ammoniates MnS3 plus can be recovered. Uses. Beryllium is used in the manufacture of alloys. Copper beryllium alloys are used in the preparation of high strength springs. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms alloys with aluminium, zinc, manganese, and tin. Magnesium aluminium alloys, being light in mass, are used in aircraft construction. Magnesium powder and ribbon is used in flash powders and bulbs, incendiary bombs and signals. A suspension of magnesium hydroxide in water called milk of magnesia is used as antacid in medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperatures, have often been used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example, in treatment of cancer. 10.7 General characteristics of compounds of the alkaline earth metals. The dipositive oxidation state is the predominant valence of group 2 elements. The alkaline earth metals form compounds which are predominantly ionic but less ionic than the corresponding compounds of alkali metals. This is due to increased nuclear charge and a smaller size. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by the heavier and large-sized members. Calcium, strontium, barium. The general characteristics of some of the compounds of alkali earth metals are described below. 1. Oxides and hydroxides. The alkaline earth metals burn in oxygen to form the monoxide MO, which is except for BeO have rock salt structure. The BeO is essentially covalent in nature. The enthalpies of formation of these oxides are quite high and consequently they are very stable to heat. BeO is amphoteric while oxides of other elements are ionic in nature. All these oxides except BeO are basic in nature and react with water to form sparingly soluble hydroxides. The solubility, thermal stability, and the basic character of these hydroxides increase with increasing atomic number from MgOH2 to BaOH2. The alkaline earth metal hydroxides are however less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. 2. Halides. Except for beryllium halides, all other halides of alkaline earth metals are ionic in nature. Beryllium halides are essentially covalent and soluble in organic solvents. Beryllium chloride has a chain structure in the solid state as shown below. In the vapor phase, BeCl2 tends to form a chloro-bridge dimer which dissociates into the linear monomer at high temperatures of the order of 1200 Kelvin. the tendency to form halide hydrates gradually decreases. For example, MgCl2.8H2O, CaCl2.6H2O, SrCl2.6H2O, and BaCl2.2H2O down the group. The dehydration of hydrated chlorides, bromides, and iodides of calcium, strontium, and barium can be achieved on heating. However, the corresponding hydrated halides of beryllium and magnesium on heating suffer hydrolysis. The fluorides are relatively less soluble than the chlorides owing to their high lattice energies. 3. Salts of oxoacids. The alkaline earth metals also form salts of oxoacids. Some of these are carbonates. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of a sodium or ammonium carbonate solution to a solution of a soluble salt of these metals. The solubility of carbonates in water decreases as the atomic number of the metal ion increases. All the carbonates decompose on heating to give carbon dioxide and the oxide. Beryllium carbonate is unstable and can be kept only in the atmosphere of CO2. The thermal stability increases with increasing cationic size. Sulfates. The sulfates of alkaline earth metals are all white solids and stable to heat. BeSO4 and MgSO4 are readily soluble in water. The solubility decreases from CaSO4 to BaSO4. The greater hydration enthalpies of Be2 plus and Mg2 plus ions overcome the lattice enthalpy factor, and therefore their sulfates are soluble in water. Nitrates. The nitrates are made by dissolution of the carbonates in dilute nitric acid. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as the anhydrous salt. This again shows a decreasing tendency to form hydrates with increasing size and decreasing hydration enthalpy. All of them decompose on heating to give the oxide like lithium nitrate. 10.8 Anomalous behavior of beryllium. Beryllium, the first member of the group 2 metal, shows anomalous behavior as compared to magnesium and rest of the members. Further, it shows diagonal relationship to aluminium, which is discussed subsequently. 1. Beryllium has exceptionally small atomic and ionic sizes and thus does not compare well with other members of the group. Because of high ionization enthalpy and a small size, it forms compounds which are largely covalent and get easily hydrolyzed. 2. Beryllium does not exhibit coordination number more than 4, as in its valence shell there are only 4 orbitals. The remaining members of the group can have a coordination number of 6 by making use of d orbitals. 3. The oxide and hydroxide of beryllium, unlike the hydroxides of other elements in the group, are amphoteric in nature. 10.8.1 Diagonal relationship between beryllium and aluminium. The ionic radius of Be2 plus is estimated to be 31 picometer. The charge upon radius ratio is nearly the same as that of Al3 plus ion. Hence, beryllium resembles aluminium in some ways. Some of the similarities are: 1. Like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film on the surface of the metal. 2. Beryllium hydroxide dissolves in excess of alkali to give a berylate ion BOH 2 just as aluminum hydroxide gives aluminate ion LOH 4 The chlorides of both beryllium and aluminium have Cl- bridged chloride structure in vapor phase. Both the chlorides are soluble in organic solvents and are strong Lewis acids. They are used as Friedel-Crafts catalysts. 4. Beryllium and aluminium ions have a strong tendency to form complexes BF4 2 AlF6 3 10.9 Some important compounds of calcium. Important compounds of calcium are calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. These are industrially important compounds. The large scale preparation of these compounds and their uses are described below. Calcium oxide or quicklime CaO. It is prepared on a commercial scale by heating limestone CaCO3 in a rotary kiln at 1070 to 1270 Kelvin. The carbon dioxide is removed as soon as it is produced to enable the reaction to proceed to completion. Calcium oxide is a white amorphous solid. It has a melting point of 2870 Kelvin. On exposure to atmosphere, it absorbs moisture and carbon dioxide. The addition of limited amount of water breaks the lump of lime. This process is called slaking of lime. Quick lime is slaked with soda, gives solid soda lime. Being a basic oxide, it combines with acidic oxides at high temperature. Uses 1. It is an important primary material for manufacturing cement and is the cheapest form of alkali. It is used in the manufacture of sodium carbonate from caustic soda. It is employed in the purification of sugar and in the manufacture of dyestuffs. Calcium hydroxide slaked lime CaOH 2. Calcium hydroxide is prepared by adding water to quick lime CaO. It is a white amorphous powder. It is sparingly soluble in water. The aqueous solution is known as lime water and a suspension of slaked lime in water is known as milk of lime. When carbon dioxide is passed through lime water, it turns milky due to the formation of calcium carbonate. On passing excess of carbon dioxide, the precipitate dissolves to form calcium hydrogen carbonate. Milk of lime reacts with chlorine to form hypochlorite, a constituent of bleaching powder. Uses 1. It is used in the preparation of mortar, a building material. 2. It is used in whitewash due to its disinfectant nature. 3. It is used in glass making, in tanning industry for the preparation of bleaching powder and for purification of sugar. Calcium carbonate CaCO3. Calcium carbonate occurs in nature in several forms like limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slaked lime or by the addition of sodium carbonate to calcium chloride. Excess of carbon dioxide should be avoided since this leads to the formation of water-soluble calcium hydrogen carbonate. Calcium carbonate is a white fluffy powder. It is almost insoluble in water. When heated to 1200 Kelvin, it decomposes to evolve carbon dioxide. It reacts with dilute acid to liberate carbon dioxide. Uses. It is used as a building material in the form of marble and in the manufacture of quick lime. Calcium carbonate along with magnesium carbonate is used as a flux in the extraction of metals such as iron. Especially precipitated CaCO3 is extensively used in the manufacture of high quality paper. It is also used as an antacid, mild abrasive in toothpaste, a constituent of chewing gum, and a filler in cosmetics. Calcium sulfate, plaster of Paris, CaSO4 half H2O. It is a hemihydrate of calcium sulfate. It is obtained when gypsum CaSO4 twice H2O is heated to 393 Kelvin. Above 393 Kelvin, no water of crystallization is left and anhydrous calcium sulfate CaSO4 is formed. This is known as dead burnt plaster. It has a remarkable property of setting with water. On mixing with an adequate quantity of water, it forms a plastic mass that gets into a hard solid in 5 to 15 minutes. Uses. The largest use of plaster of Paris is in the building industry as well as plasters. It is used for immobilizing the affected part of organ where there is a bone fracture or a sprain. It is also employed in dentistry, in ornamental work, and for making casts of statues and busts. Cement. Cement is an important building material. It was first introduced in England in 1824 by Joseph Aspdin. It is also called Portland cement because it resembles with the natural limestone quarried in the Isle of Portland, England. Cement is a product obtained by combining a material rich in lime CaO with other materials such as clay which contains silica SiO2 along with the oxides of aluminium, iron and magnesium. The average composition of Portland cement is CaO 50 to 60%, SiO2 20 to 25%, Al2O3 5 to 10%, MgO2 to 3%, Fe2O3 1 to 2% and SO3 1 to 2%. For a good quality cement, the ratio of silica to alumina should be between 2.5 and 4 and the ratio of lime to the total of the oxides of silicon, aluminium and iron should be as close as possible to 2. The raw materials for the manufacture of cement are limestone and clay. When clay and lime are strongly heated together, they fuse and react to form cement clinker. This clinker is mixed with 2 to 3% by weight of gypsum to form cement. Thus, important ingredients present in Portland cement are dicalcium silicate, tricalcium silicate, and tricalcium aluminate. Setting of cement. When mixed with water, the setting of cement takes place to give a hard mass. This is due to the hydration of the molecules of the constituents and their rearrangement. The purpose of adding gypsum is only to slow down the process of setting of cement so that it gets sufficiently hardened. Uses. Cement has become a commodity of national necessity for any country next to iron and steel. It is used in concrete and reinforced concrete, in plastering, and in the construction of bridges, dams, and buildings. 10.10 Biological importance of magnesium and calcium. An adult body contains about 25 gram of magnesium and 1200 gram of calcium, compared with only 5 gram of iron and zero point zero 0.06 gram of copper. The daily requirement in the human body has been estimated to be 200 to 300 mg. All enzymes that utilize ATP in phosphate transfer require magnesium as the cofactor. The main pigment for the absorption of light in plants is chlorophyll, which contains magnesium. About 99% of body calcium is present in bones and teeth. It also plays important roles in neuromuscular function, interneuronal transmission, cell membrane integrity, and blood coagulation. The calcium concentration in plasma is regulated at about 100 mg per liter. It is maintained by two hormones, calcitonin and parathyroid hormone. Do you know that bone is not an inert and unchanging substance, but is continuously being solubilized and redeposited to the extent of 400 mg per day in man? All this calcium passes through the plasma. Summary. The S block of the periodic table constitutes group 1 alkali metals and group 2 alkaline earth metals. They are so called because their oxides and hydroxides are alkaline in nature. The alkali metals are characterized by one s electron and the alkaline earth metals by two s electrons in the valence shell of their atoms. These are highly reactive metals forming monopositive M plus and dipositive M2 plus ions respectively. There is a regular trend in the physical and chemical properties of the alkali metal with increasing atomic numbers. The atomic and ionic sizes increase and the ionization enthalpies decrease systematically down the group. Somewhat similar trends are observed among the properties of the alkaline earth metals. The first element in each of these groups, lithium in group 1 and beryllium in group 2, shows similarities in properties to the second member of the next group. Such similarities are termed as diagonal relationship in the periodic table. As such, these elements are anomalous as far as their group characteristics are concerned. The alkali metals are silvery white, soft, and low melting. They are highly reactive. The compounds of alkali metals are predominantly ionic. Their oxides and hydroxides are soluble in water, forming strong alkalis. Important compounds of sodium include sodium carbonate, sodium chloride, sodium hydroxide, and sodium hydrogen carbonate. Sodium hydroxide is manufactured by Kastner-Kellner process and sodium carbonate by Solvay process. The chemistry of alkaline earth metals is very much like that of alkali metals. However, some differences arise because of reduced atomic and ionic sizes and increased cationic charges in case of alkaline earth metals. Their oxides and hydroxides are less basic than the alkali metal oxides and hydroxide. Industrially important compounds of the calcium include calcium oxide, lime, calcium hydroxide, slag lime, calcium sulfate, plaster of Paris, calcium carbonate, limestone, and cement. Portland cement is an important constructional material. It is manufactured by heating a pulverized mixture of limestone and clay in a rotary kiln. The clinker thus obtained is mixed with some gypsum 2 to 3% to give a fine powder of cement. All these substances find variety of uses in different areas. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. That's all for today. Thank you.